Hi, thank you for your time. As we discussed in my videos, today we were supposed now to start Matlab, whereby we were to discuss 6-step commutation of a BLDC motor. As we discussed that a BLDC motor is usually controlled by a trapezoidal. Remember on the trapezoidal simulation, the back EMF video where we had some simulation of a trapezoidal wave of a BLDC motor, and we discussed that we use MOSFETs to switch on and off the 3-phase inverter so as to energize the stator windings differently. In the process, the rotor starts to rotate. And we say that at any given time, we have a different commutation logic that is dependent on the sector at which the BLDC motor is. When I say the sector, I mean the position at which the rotor is at a given time, because we have 6 sectors which are 60 degrees apart. And today our main focus, we're going to have some simulation, and we're going to assume a static switching. We're going to switch only A, and C. We're going to switch A and C on and have some simulation of BLDC motor. The first thing we need for us to model this, we need MOSFET. I will prepare a small video to explain in the deeper details how MOSFET function, but just know this: MOSFET is a switch that turns on and off depending on the signal at the gate. Remember this video we discussed about the resistors, they have the same concept. Therefore we need 6 switches, 1 2 3 4 5 6 of them. You go to library, it is loading. This time I'm going to use Simscape. The Simscape I'm using electrical. Then I need semiconductors and converters. We have a lot of switch here. We have GTOs and GBTs. I'm using a MOSFET. Okay, we're going to use 6 MOSFETs to have 6 control in our commutation logic. This is my first MOSFET. Let me rename it as AH. That is our first switch. When I say AH, I mean A is the coil, that is our stator. We have A, B, and C. Don't worry, this diagram is not very clear. Then H means it is high side. We have a positive side and lower side. That is, we're going to use L to represent the lower side. Therefore, if I copy this, I have now, instead of a H, I have an L to represent it is lower side, meaning it is negative. Positive high, let's assume H for positive, L for negative. This is my S2 switch. This is my S1, S2, S3, S4, S5, S6. I'm using the image from my previous video. Then I need to copy this twice and rename. We have this is a BH, that is our S3. This is our BL, that is our S4. This is our CH, that is S5. This is our CH, that is CL, that is S6, switch number 6. Okay, then we need a DC voltage source. Therefore I need a voltage source here, and I will use 100. Let me use 100 for now. Okay, then in this video I'm just going to model this section and a small section here. Then in my next video I'll go deeper in now how to model a sensor and a full commutation logic. Therefore, put this aside. You connect this to one side of a MOSFET, this to this. Same applies on this side. Yeah, I think that's fine. I think that's fine here. Let me have more space because we need more space here. I think that's fine. Those are my 6 MOSFETs representing this section here, or 3-phase inverter. Then next we need our BLDC motor. You go back to library. We are using electromechanical. There's a combination of both electrical and mechanical side, and we are going to use a permanent magnet. For now our focus is BLDC. Later I will use PMSM. And I said in there's a video I created on how to simulate back EMF on the BLDC, and we said for us to get a 3-phase, you just right click, select Simscape block choices, then you expand to get A, B, and C. Then this side is a mechanical conserving port for rotational element. Therefore I need mechanical rotational reference here. Then I need on this side, we need now, because this is our shaft, we are going to supply current on ABC, meaning our shaft will rotate. And I said whenever there's a rotation, whenever shaft is rotating or any part is rotating, it always have moment of inertia, and we capture the moment of inertia using inertia block. And I'm going to assume for now, for purpose of simulation, it has a 0.2 moment of inertia, kilograms meter squared moment of inertia, that I can connect directly here. Then we need a solver. I said the only place we don't use solver is when you are dealing with power electronics, and we said we always use GUI. Therefore, in our solver, I'm going to use a local solver, backward Euler, and I'm going to use a sample time of 1e-5. Let me use this type of solver. Then that's we have set to go on that side. Then whenever there's a rotation here, we can get two types of data. We can get angular acceleration, at the same time angular displacement. For us now to measure the speed of the rotor, we need a sensor that is called rotational motion sensor. You can go to library, foundation here, mechanical, rotational elements. We need sensors. For mechanical sensors, we need ideal rotational motion sensor so that we can be able to measure angular velocity. W is for the angular velocity, A is for the angular acceleration, is for the angular displacement. We connect this to A port on this side. Then at C port is our conserving port that we need to connect with our rotational reference. On W we get our angular velocity and angular displacement here. We need to convert this one from P because we need we're going to have a scope here where we are going to display. For the first one, we're going to display speed. The speed of our BLDC. Let me show the name. You just click, you go to format block name on. Therefore, then this one we need another one to show the angular position. This angular position will enable us to determine the sector at which our rotor is, first sector or second or third. Therefore, then you can't connect these two. We need P to Simulink converter. Same case applies on the bottom side. These are now basics. We can now be able to define the units we need. I don't need to see. Okay, we can be able to define the units we need here for the speed. If you don't know the units, always use 1 most of the time, but for me I need speed to be, I need the units for the speed to be degrees per second. Then for the angular position, I need degrees there. So that will be very important as we model our Hall sensor to measure the sector at which our rotor is. We're going to use this data. It will be very, very important as you progress. Then I can call this theta. That varies from 0 to 360. Then after that, we can have now define our BLDC parameters. We are going to let's use a permanent flux linkage of 0.5513. These are the parameters we can get from the motor we are using. This one to be default. For the mechanical, let me use rotor inertia of this is the internal rotor inertia, 0.2 for the damping. I think we are done with the mechanical side. The reason why this one is called electromechanical has both mechanical side and electrical side. Let's now model the electrical side. This is first phase that goes to the first switch. This is a first switch pair. The second one should go to this one, and the third one should go to this. Then we need electrical leaf lines. because we need to connect neutral to electrical reference. Then we need to measure the current and voltage supplied to the BLDC. Okay, therefore I need to go back to library. I use sensors and transducers. I need a 3-phase current sensor. Add block to the model. It is. I go back to the library, then use a 3-phase voltage sensor. Okay, this one. I have selected the wrong one. I need this voltage phase. Yeah, this one. Yeah, that's fine. As you can see, as you said, if you want now to have three phase indicated here, you just click, you go to Simscape, block choice expert. For the current, we need to connect here. You can delete connect here, then A to the first set, B to second set, C to third set. Can make it neat a little bit. Yeah, I think that's better. Then here is how you're going to have our measurements at this port of the current. The same case applies to the voltage sensor. We connect A to the first phase, B second, C to third. Then we need a P to S because we need to monitor the current here. This is called 3-phase current. I can delete this now, I don't need it. Then we can zoom in here. Let me make it a little bit organized. Yeah, I think we are done on that side. Then we need a scope to measure the voltage. Then you connect A to B and B to C because we are not taking any measurements here, and they put a reference like a ground. Therefore, it will be measuring the voltage here with respect to this point. The same case here with respect to this point. Okay. Then on the MOSFET, I forgot to define the parameters of the MOSFETs before you copy, but no worries, we can just define very fast one by one. Always define the parameters of the components before you copy, so that you don't have to waste your time defining all the components one by one. These are the parameters. You can Google of them. Some of them might understand them, but most of the time, personally, I use the parameters provided by the data. Yeah. Then after that, we need now to supply. Remember, I said we have to supply a signal here so that the switch can close and allow the current to flow. Therefore, we need I need to have a vector made of constants. Let me take a constant, and I'm going to use this will be our switching pattern that will be made of 6. There are 6. We need to provide each either 1 or 0. Therefore, I'm going to have a vector of, we need to switch A and C. That is from my previous one was this one's supposed to be 1 and 1, or this 0. We want to switch first one, the first. Therefore, I need 1 this point, 0, 0, 0, 0, and 1, like that. Then for us to distribute all these values here, we need to go back to library. You select signal routing, use a dmax is used now to distribute various signals to various blocks. It receives one, it will receive 10001, then distributes 6 times. Therefore, I have to set dmax to 6 ports. Yeah, like that. That's better. Then we need instead of having a continuous lines from here, they might overlap. Let me use just a go to. You can resize it, make it smaller. Then we can copy, connect, copy. We have now to rename. This one is supposed to be AH. This is AL. You have to rename as per sequence. This means it will now take 1 to AH, 0 using AL at this point. Lastly, CL will take 1 to this point. Therefore, you have now to copy this. I'll go to you take now the from I'm using just right click and drag. We need now P S to P, because this one is a Simulink. We need to convert to physical. Now we can assign easily. Make sure they connect. Allows you to get the result accurately. That's how you model your switching pattern using Dmax, so that you can be able to distribute your switching pattern to various MOSFET switches. Okay, then I think we are done. Lastly, now we can now combine this one to make it a simpler using subsystems. Therefore, I need to let me rearrange a little bit here, because I need to select all these ones except this side. I want to select all of these so that I can form a subsystem. Three dots, the first one. We are forming now a subsystem, and to be simpler now, we can be able to rearrange this subsystem like that. This one is three phase inverter. That's how you model a three-phase inverter using MOSFETs. This one is you just go inside this, you can rename as a switching pattern. Then these ones are supposed to be the first phase, phase A, phase B, phase C. You can see now our model is a bit simplified. Still, if I want, I can still also combine this to form a subsystem. Lastly, before I simulate, you go to modeling gear icon here. I need now to change the solver or use a fixed step, not a variable step. I'm going to use a fixed step. Start time 0.2 seconds. Then select OD1 EULA. You can, if you just want to understand, if you want to understand all of these, like Ligikuta, Hyun, where we use them, you can go to help. They will explain under which circumstances do you use OD8 or OD14X for extrapolation. Otherwise, I can make a video for you to illustrate at which circumstances you use one of them, because the solver, depending on the type of solver you select, it will solve differently. Mostly, but not many scenarios. For now, I can use OD1. Lastly, for me to simulate, I have to log the data here. I want to log this data and to log this data. This means, logging means the data here will be captured. And we are done. Let's now simulate. You go to Matlab. If you now go back to Matlab, I've already created a script that will be used to animate our model. And my script is animate rotor. That's my script. I'm going to share this script with you on the video description. Use it, just run the script. You only have to change here. you have to put the name of your model. When you save your model with maybe this has to be okay. This one have to change here. If your model name in the Simulink is just write and run the model here. Write the name of the model, or you can select run, and it will execute the command you enter. It will open your model. It solves the model, generates a small graph that has both rotor and stator. A, B, C, those are stators, then the middle one is rotor. You just have to press one button for the animation to take place. Yeah, you can see we have energized A and C, but because we are not switching, remember we are not switching here, it is just one. The reason why A and C remains energized, as you can see, A is high for red, C is low, because we said AH and CL. If you go back here, we said it is an AH receives 1, CL receives a 0. 0 means low. The reason why we have A is high, but this one is low. And this motor doesn't continue rotating because we have energized A and C continuously. Now, when we move on to our next video, we are going now to swipe, now energize B with an A, and we're going to change the stator windings, how we energize. In the process, the rotor will start to spin. As you can see now, it has just spinned and stopped because the type of switching pattern we have is called static switching pattern. We are just applying voltage continuously to stator windings of A and C. That's all I have today for you. Let's meet in our next video where we are going now to model the remaining section. We're going to model a Hall sensor to measure the sector position. Then we're going to model complete commutation logic that has 6 steps. Thank you. Subscribe. Stay tuned.